Thanks, Matt. So yeah, like Matt said, I research planet formation. And if you're not super familiar with planet formation, you might not know that there are actually two different main theories on how planets actually get formed in the first place. And they really couldn't be any more different from each other. So in this talk, we're going to cover both of those. But before we do that, we're going to have to lay some groundwork. So star formation is inextricably linked with planet formation. So we're going to have to do a little bit on that first. And then we're going to talk about the environments in which stars are born. Protoplanetary disks is what that's called. We'll get to that. And then we're going to do a brief overview of these two different formation pathways and talk about them in more detail once we've got some notion of what's going on. Can everyone hear me okay? Can you hear me at the back? Cool. All right, so when a star is born, we start out with a huge cloud of gas and dust. And due to gravitational effects, parts of that cloud will clump and coalesce. You maybe can't see it so well in this lighting, but this this middle right one is kind of okay. You can see that there's streams and chunks of the gas that looks denser than other parts. And those denser clumps will collapse further to make stars, or the beginnings of stars. But as each clump collapses, it begins to rotate faster and flatten out until you get this bottom stage. And the reason it rotates faster is because every cloud in space, basically everything in space, will be rotating at some kind of speed to begin with, because it's really unlikely that a cloud just sits there without any motion whatsoever. It would just be a very unlikely series of events for that cloud to come into existence in the first place. And as an object that's spinning collapses, we know that classic example of an ice skater on a rink, or a figure skater on an ice rink. She spins with her arms out, she pulls her arms in, and she spins way faster. That happens with the disk. So it spins, it collapses, it spins up, and it flattens out. So we're left with a star surrounded by a disk. And of course, eventually, that core is going to continue to collapse, and nuclear fusion will occur, and you'll be left with a star. But what we really care about, we don't really care about star here. Sorry, anybody who likes stars. What we really care about is this stage here. This is called the protoplanetary disk surrounding the star, and that's where planets are made. Oh, I forgot I did this. So I like to show images alongside the graphs, so real images, real photos, just so you can see I'm not just making all this up. These things actually do exist. So on the left, there's an image from the Orion Nebula, and you can see these streams, these filaments. If I turn the lights up, you can see it better. Okay. You can see, yeah, see, it's much better. You can see these filaments throughout this region, and these hot spots, these brighter parts of these filaments are where star formation is occurring. And actually, there's a lot of stars already formed up at the top, where you can see it's super bright. And in this image over here too, you can see a similar effect. You can see the gas has these. It's not like this uniform cloud. It's got clumps, it's got lumps, it's got filaments, and that's what allows stars to form. And the stars forming is how planets form in the first place. Don't see the light switch anymore. Okay. All right. So moving back to our protoplanetary disk, this is an artist's rendition of what it looks like. So you can maybe see the star is a really tiny dot in the middle there, and there's this huge expanse of gas and dust, and it's not very smooth. Well, it can be, it looks smooth, but there are typically rings and gaps. It's very structured. Importantly for our discussion later on, it's really hot close to the star, which makes sense, you're near a star. And as you move out in the disk, you A, become less dense, there's less material, and B, you become colder because you're further from the star's radiation. Like I said, it's got lots of gaps and rings and spiral arms. Oh, not always, but it can. And this will also be important for any sort of formation pathway we talk about. Relatively speaking, protoplanetary disk is fairly short-lived. I said a few million years, but typically a few tens of million years at most. And that sounds like a really long time. The stars live for billions of years, okay? So it's comparatively quite short. So any formation pathway we talk about has to be something that happens on a cosmic scale quickly. And as before, here's a real-life image of what one of these objects looks like. This might not be super impressive for some of you, but this kind of thing they only really started being able to make images like this when I started my undergraduate. I'm not that old. So it's quite recent that we've been able to see things like this. You can actually see the star in this image because it's being obscured by by the disk itself. But you can see that it becomes brighter towards the center because it's hotter and denser, and then you've got these rings like I mentioned before. So this is just one example of a protoplanetary disk. We've got about 40 or 50 really nice images like that. Well, maybe 20 really nice ones and 40 or 50 okay. And those are possible because of ALMA. That's the Atacama Large Millimeter Array. It's a radio telescope out in the desert. Okay, so we're going to talk briefly the top-down and bottom-up processes for comparison. So the top-down process, just so we're on the same page, you start with a big cloud of something, and you condense it to make a planet. So you start big, you collapse small. And the bottom-up process is kind of the opposite. You start with grains, maybe micron size, and they collapse together to make centimeter-sized grains, and they smash together to get bigger and bigger until you form a planet. So you go either start hundreds of thousands of kilometers wide and collapse down, or you start micron-sized and move up. And they really can't get any more different than that, but we're not quite sure which of these forms every planet yet. So we're going to talk in a little bit more detail about each of them. So the top-down planet formation pathway is more formally called gravitational instability. And it'll be kind of obvious why it's called that in a moment. You'll have to excuse my MS Paint diagram. I thought it might make things a bit clearer. I've got a snapshot of the disks that we had earlier, so you can see which part I've drawn here. So we've got our star down there, and then the light gray is just the disk. And in dark gray, I've shaded a region of the disk, so just a section of the disk that I've arbitrarily cut out. And if we look at the forces that are acting on that region of the disk, we've got the gravity. I've called it self-gravity because that's the gas and dust in that region being attracted to itself and wanting to collapse further. That wants to pull it down into a chunk and wants to collapse. The thermal pressure, so the heat energy in that region, tends to expand the region, so it opposes collapse. And we've also got centrifugal force opposes collapse. To explain that bit, I've got a picture of a roundabout. When I see my nieces, we have this game where I'll put them on the edge of the roundabout, and I'll spin it real fast until they get thrown off. Their mother is less of a fan of that than they are, but I'm sure we can all visualize it. The centrifugal force has a tendency to throw things out and rip things apart. Well, hopefully not that last part if you're on a roundabout. And so our little chunk has got all these forces acting. It's got gravity wants to pull it in, and thermal pressure and centrifugal force wants to rip it out. And the net effect of all of that is that if the disk is massive enough and cold enough, those are relative terms, we can get gravitational instability, where parts of the disk will collapse, and this happened on a global scale, and we get spiral arms. And I know what all of you are thinking as you sit there and look at these beautiful simulation images. Those aren't planets. Those are spiral arms, and yes, they're pretty, but they're not planets. And the reason why they're not planets yet in this simulation is because as the chunk collapses due to gravity, that's going to release gravitational potential energy, which will heat up the spiral arm again. And as we remember, thermal pressure tends to oppose collapse, and so you can be stuck in this quasi-stable state where your spiral arm kind of collapses and expands and collapses and expands, and just stay like that indefinitely, unless you have efficient cooling. So if your system can cool, then as you collapse, you release gravitational energy, which heats the chunk, but that's dissipated throughout the disk or cooled off through radiation into space, and you can get something called fragmentation. And when that happens, we start out with a bunch of fragments. You can see that they've collapsed parts of each of the spiral arms that they're in. Not all of them will be long-lived. The tidal forces talk later might be good because a lot of them will be ripped apart by tidal forces or just smeared out by the disk. But some of them, as you can see in this simulation by some of my colleagues, will survive. Don't mind the fact that they're called George and Ringo. John made a bet that he could name them after the Beatles. And that did, in fact, make it into a paper, so turns out you can do that. Yeah, so some of the fragments, most of them will die, but some, these two here, George and Ringo, they survive long enough that they can eventually become planets. Okay? You may be less impressed with this image than the previous ones. I know it's quite blurry, but this is another real image of a protoplanetary disk, and this one shows spiral arms. Now, it's not guaranteed that these spiral arms are formed via gravitational instability. There are other processes, like planets interacting with a disk, that could make it, but it's a good sign. Okay. Moving on to the other formation pathway, the bottom-up planet formation, core accretion, starts, well, before we get into that, we're going to talk a little bit about the environment of the disk itself. So we start, if we look at a more detailed picture of the disk, we've got, like we said, very hot in the middle and very cold on the outside. And what this means, in effect, is that close to the star, you're left with rocky material and silicates, things that can exist in solid form at very high temperatures, and other things like water vapor or carbon dioxide, or things that are normally in a gas at high temperatures, will be in the gas phase. So you've got some in the dust, but most of your stuff is in the gas phase. And as you move further out in a disk, and you move to the colder regions, the water can freeze out onto the dust grains, and you end up with a lot more material in your solids than you have in your gas. Well, you still have more gas and solids, but you end up with comparatively more solids than you do interior to the snow line. You'll see why this is important soon, trust me. Just an important note, you don't just have one snow line. It's not inside the snow line, everything is gas, and outside snow line, everything's frozen. You'll have a different snow line for each compound. So water will freeze at a different temperature to carbon monoxide, will freeze at a different temperature to carbon dioxide. So if you visualize one of these for each compound, that's what you have. But water is one of the most important ones because water is incredibly abundant in space. Okay, so the important take-home is there's a lot more solid stuff to work with further out than interior to the snow line, even though if you look at the bulk density of the disk, the gas and the dust, you get more dense towards the star center. Okay, so bear that in mind for the next part. And that's an artist's impression, by the way. This one is not a real image, much as I would like it to be. Okay, so this is a rapid-fire overview of core accretion, which you'd be glad to know is a little bit more straightforward than the spiral formation from before. So we start out with small grains. We start out at about 3 o'clock and work counterclockwise. You start out with small grains that are like micron size, and calling these dust is really appropriate. And they will coagulate in a process called pebble accretion. So the dust grains will smack together and they'll stick together. They tend to have very porous surfaces, so they smack and they stick and they grow into these clumpy aggregates. And they'll do that until they hit about a meter in size. That's when we stop calling it pebble accretion. These pebbles themselves will smash into each other and stick together again. This is going to be a bit more violent once they hit about a meter in size because they can smash and break each other, or they can bounce off each other. So you're going to have some meter-sized, calling them meter-sized object, a pebble isn't quite appropriate, but some meter-sized rocks, say, will smack together and explode, and you'll be left with a bunch of dust grains floating around. But some of them will smack together and stick, or they'll pick up smaller dust grains until they hit about 1 kilometer in size, at which point we call them planetesimals, because they're approaching the point of being a planet. Now these will continue to grow by either sweeping up the smaller dust particles from prior collisions or from accreting, smacking into other planetesimals, until they hit a point, so at this point here, say, this bottom left slice of the pie, where something called runaway accretion can occur. And I say can occur because it doesn't always occur. So once you've hit a certain critical mass, it's about 10 Earth masses, your gravity becomes strong enough that you start to pick up the gas that's surrounding you. So far, you've just been accreting by smacking dust grains together, by smacking rocks together and becoming a really big rock. But at this point, you can also take in gas. And the thing is, once you become heavy enough to absorb, to accrete gas, you're still heavy enough to accrete gas, but now you've got more stuff. So you become even better at accreting gas, and that's why it's a runaway phase. You grow and grow and grow until you effectively run out of gas in your local region. But this doesn't always happen. So interior to the snow line, we haven't got enough solid material for the core to become big enough for runaway accretion to occur before this gets dissipated into space, because like we said, relatively speaking, it's a short time. But outside the snow line, your core grows really, really fast, all the material in your vicinity, because you grow your core big enough that you can sweep up all the gas, and you end up huge. So we can see in these snapshots of the composition of the gas giants, their core is quite small, but they've accreted so much gas material that they've grown fantastically large. And I'm afraid because this happens on a scale of microns, meters, to even kilometers, I don't have a photo of this happening. But I do have what I hope will be a convincing photo that it's an all right theory, because I have an image of the solar system planets, and the snow line would be about here. So we can see interior to where the snow line would have been, we have rocky planets, and exterior to where the snow line would have been, we have the gas giants, where the runaway gas accretion has happened. And so core accretion is a great way of explaining these planets. Okay. Which comes to the question of which one of these theories is actually correct. And that's a tough one to answer. So the gravitational instability, like we said, you need to be really massive and really cold. So you can only really happen for really massive disks, but young disks, we believe, all start out very massive, so that's okay. They lose mass over time, but they start out quite heavy. And by really massive, we mean maybe 10, 20% of the mass of the star. Because they have to be, we'll get to the cold part in a minute. It easily forms giant planets, so like Jupiter size, beyond 10 Jupiter masses. In fact, that's what it's too good at doing that. It can't make terrestrial sized planets. If you're forming in a way similar to how stars form, it's very hard to make a very small object, because if you're big enough for gravitational collapse to occur, you're generally quite big, and you're going to end up with quite a large planet at the end. Although these can be tidally disrupted, these can be stripped of material to make them smaller, we generally say that you have to be about Jupiter size or above. And you easily form planets that are really far out in the system because it's really cold there, and that's where gravitational instability works the best. But you don't form rocky planets by gravitational instability. You don't form planets close to the star. Core accretion generally explains things really well. You can form small or massive protoplanetary disks. It doesn't matter. So you could happen early on or later in the system. You can form rocky giants. You can form giant planets. Sorry, rocky giant. You can form rocky planets or giant planets. But there's one case that the system really finds it hard to explain, and that's really big planets really far out in the system. If I go back to our diagram here, we can see that the planets get smaller as you get further out, which in part is because there's less material the further out you get in total, gas and dust combined. And also something that core accretion has to contend with is that your collisions happen slower the further out you are. So you have less time, you have the same amount of time, you have fewer collisions to make your planetesimal really big. So it's really hard to explain. Giant planets formed outside there, really far out in the disk, and these do exist. We have a few examples of them. So the general consensus is that core accretion is typically a good explanation for most planets, but it doesn't really explain all of them. Across the scientific community, you'll find some people that will say that core accretion can definitely explain all planets as long as you make all these changes. You'll find a very small number of people who try to say that gravitational instability can explain all planets, but that's very left field. But this seems to be the general consensus, that core accretion is good for explaining most of the planets. There are a small number of outliers that are really hard to explain with core accretion that would very easily be explained with gravitational instability. So which one is correct, in my opinion, is both of them, but in very different regimes. They're quite complementary to each other in terms of which areas of parameter space they cover. So we'll just stick up the summary slide of the top-down and the bottom-up processes. And I think that's about time. Okay? Thank you very much.
I love these pretty pictures of like the
they're fantastic.
simulations. Always so incredible. Does anyone have any questions for our speaker? Yes.
You might have already said this, but
That's okay.
So with the runaway accretion, as you take on dust and gas, you increase your size, and so the gravity increases. With our terrestrial planets, why did they stop growing?
So they stopped growing because they ran out of time. So the disk, if I go to a picture of our disk so we have it to look at. So our disk looks like this early on in its life. It's got gas, it's got dust, it's got all these lovely things. But over a span of a few million years, a few tens of million years, you've got radiation from the star, you've got winds from the star. Maybe if you're in a very busy neighborhood, you might have winds from other stars or radiation from other stars. They'll blow the disk away. It's just gone. So by the time a rocky planet would get big enough for core accretion, for a runaway accretion to happen, there's no gas left to accrete. Or it might also run out of dust before it can hit that point, because the dust will also be blown away, but it's typically you've run out of gas first. Thanks for the question.
Anyone else? Yeah, at the back.
There's been a few kind of asteroid missions, and there's going to be like a sample return mission, and they tend to find this quite gravelly in an asteroid.
Uh-huh.
Does that have implications on maybe bottom-up accretion?
Yeah, so you said gravelly, right? That's a really good description. So have I got the, yeah, so we start out with small grains will smack together, and because they're just smacking into each other, and they generally, the heat from that process might melt them a little bit and they'll stick together, you end up with this, I should have put a picture in, you end up with this really funky shapes where they basically form fractals, basically, of weird grains just stuck together into this weird mess. And so asteroids, people have this picture of asteroids as being a solid mass, but they might not be. They could just be a weird, very loosely bound aggregate of lots of smaller bits just stuck together with duct tape, basically. I don't know if that answered your question, but it's a good sign that this is maybe what's going on.
So when you say that, like from Jupiter's acceleration lectures, gas giants, does that technically mean that kind of you can, because it's probably not going to happen because the gravity is quite strong in it, but if there was no gravity like Earth, would the people supposed to like fly through it?
Yeah, I mean, they're just a very, really super, super thick atmosphere. It might become liquid further down. I don't know an awful lot about the internal structure.
About the rings, can you go back a few slides?
Tell me when to stop.
That.
Yep.
So in the star in the middle, is that how like and the outer bit, is that how the rings are formed?
Is what how the rings were formed, sorry?
So you have the star in the middle,
Uh-huh.
and then you have the dust and ice on the outside. Is that how the rings of planets are formed?
Oh, the rings of planets. There are a lot of theories about why the rings of planets are formed. But whichever formation pathway you have, whether it's core accretion or gravitational instability, they're going to sweep up a lot of the stuff in their immediate vicinity, but they won't sweep up everything. And yeah, it is quite similar to the disk around the star. When things collapse or accrete together, they tend to form flat disks, because that's how conservation of angular momentum works. You might also have moons might get torn up in the orbit of these planets and form rings that way. That's a common idea for how they might get made. But yeah, it is a similar sort of idea that you can form these flat disks, flat rings around different objects.
Cool. Oh, there you go, yes.
Looking at our own solar system for a moment, you put the planets in the order that they are now. I think I was reading an article recently which suggested they may not always have been in that order.
Yep.
And Jupiter in particular has been the big bully of the solar system and might have existed or formed much closer to the sun and caused disruption in the ordering and the way that even perhaps the planets have formed. Does this serve to complicate the issue as far as your two alternative theories are concerned?
I don't know an awful lot about the early dynamics of our solar system, but planet migration is a massive complicating factor in basically every other solar system we've ever looked at. So when we first started coming up with our planet formation theories, we had this core accretion model, and we were like, yeah, that's done and dusted, easy peasy. Look at how well it explains our solar system. And we're like, what we expect to see, based on this model, is rocky planets close to the star and gas giants further out. And the very first planet that was ever observed around another star was a hot Jupiter. It was, yeah.
Goes into its star.
Yeah, it was a Jupiter-sized planet really close to its star, and we were all like, what? And the general consensus is that planet migration is really important. So these mechanisms, they can explain where planets form when they're first born, but it doesn't tell you anything about where they end up or how they migrate throughout the disk. I don't know an awful lot about planet migration, but yeah, it really complicates how we understand them.
Is your particular field of expertise exoplanets then, is it?
Yeah, I look specifically at gas giant formation by gravitational instability. Yeah.
Another question at the back, yeah.
Just to kind of what you said, planet migration could it affect the process of planets that haven't completely formed yet to cause these disks in the first place?
Could you repeat the question, sorry?
When the gentleman was talking about planet migration, The rings we've got on our planet could have been formed by planet migration in the first place. Whilst that planet was forming, that created the disk, because it never got the opportunity to pull the mass into the centre.
The rings around the planets. Yeah, I mean, well, the planet migration early in our system was super important, even for Earth, because that's why we have our moon. We had two planet-sized objects collided, and one of them became the Earth, and the leftovers became our moon. So yeah, the migration and things being ripped apart, like, people have this kind of image that solar systems and space are really peaceful. You've got gas clouds, you've got this lovely picture of the disk, but they're really violent places. You've got planet-sized objects collide with each other, and that rips everything apart and messes everything up. So yeah, them moving is really important.
Wonderful. Okay, so I think it's probably time to have a bit of a break, some tea and biscuits, and then come back to hear all about tidal forces from Brian. But before that, can we thank Maggie again? So there's a good chance we might get some more questions. Do you want
No,
to
I can stick